Hello, everybody, and welcome. Thank you for joining us. My name is Ray. I'm the Marketing Director of Starview International and will be your host and facilitator today. At the bottom of your screen, you should see a Zoom toolbar similar to what I have shown here. You may submit any questions you may have throughout the session, and we will answer them during the Q&A session. Should you run into any difficulties, please let us know in the chat window and our panelists will assist you. This is our agenda for today. Our panel of speakers today are Yuju, Managing Director of Starview International, David, CTO of Define Technology, Babak, Product Management Director Lightbits. We also have our team of panelists. From Starview, we have James, Systems Engineer, Chan, Consulting Systems Engineer, Alfred, Regional Sales Director from Lightbits, Ola, Head of Operations and Marketing from Define Technology. So without further ado, let me hand over to our first speaker, Ju, who will be introducing you to Starview's 1STACK private cloud offering. Over to you, Ju.
Thank you, Ray. I will start to share my screen right now. So I just want to confirm that you guys are seeing my presentation slide. Ray, can you confirm?
Yep, you can.
Okay, very good. Okay, so welcome everyone. For people coming in from Singapore and Asia, good afternoon. And for the rest of the people from Europe and the Middle East, good morning to you guys. So what I am going to talk about today is 1STACK, which is one complete stack of a solution that allow us to build a private cloud. So you may ask, what is a private cloud? You may be familiar with the cloud services of Amazon or Google. They are the public cloud providers. So services from such companies allow you to order compute, storage, and network resources. They will provision it in a mere minutes, and then you can load in your applications or workloads very quickly. So if any of those resources are not enough, you can scale up or you can scale down as needed. Such flexibility gives you the agility to roll out applications very quickly. So what if your business, due to cost, compliance, or regulatory reasons, do not allow you to use a public cloud? Well, then your alternative is to build your own private cloud and with the same kind of flexible features. So 1STACK is your alternative, and it is a full complete solution stack that includes server hardware, open source software, ultra high performance storage, and support services to make your journey into the private cloud a success. 1STACK is a Starview brand. We partner with Define Technologies and Lightbits to make 1STACK possible. Together with Starview, Define Tech is our partner for ongoing OpenStack support and advanced use cases of 1STACK. For example, high performance computing, virtual desktop infrastructure, genomics, etc. And Lightbits is our partner for scaling IOPS to the millions so that we can support very high performance applications. Before I dive into the specifics of 1STACK, this is one slide on Starview, the company behind 1STACK. I am the co-founder of Starview, and together with Wilson Tan, we started Starview 11 years ago in 2010. Over the years, we won numerous awards and accolades. We own patents on optical transceivers. When we first started, our vision was to develop programmable transceivers. So with programmability, we then have the flexibilities for our transceivers to work on any brands of switches or routers, whether they are Cisco or HP, Arista, etc., etc. We then began our distribution business, representing various companies and brands that we can combine with our transceivers so that we can offer it as a complete offering. So that led us to data center infrastructures and bare metal switches. And when we were serving our data center customers, we found that cloud providers were building very large and complex network, compute, and storage infrastructure, all based on bare metal using open source software. So one interesting fact that we found is that the large brands are missing from the entire solution stack. And because these large brands are not there, the cloud operators can avoid the high capex. So that led us into private clouds, and here we are introducing 1STACK to you. The cloud has been gaining a lot of traction in the last few years. Compounded growth of companies moving to the public clouds has made companies such as AWS, Google, or Microsoft the world's largest provider of public clouds. And with virtualization, infrastructures can be very efficient, very agile, and scalable. Virtual machines and resources are provisioned with a few mouse clicks and made available in just a few minutes. No longer do we need months to buy, deliver, and set up physical server hardwares. And with modern software development and containerized architectures, services can be delivered at very high cadence. Capacities can be added linearly to the platform when required, without the need to do upfront capacity planning like in the past. In this unusual situation that we are seeing today, the COVID pandemic has actually accelerated our shift into the cloud. And it has made cloud no longer an option, but really a necessity for many, many companies out there. So you want to build a private cloud. Where do you start? Whether you are considering commercial cloud software, like VMware, for example, or use the open source OpenStack, it is a very complex exercise. For many of our enterprise, government, or service provider customers, the expertise and talents needed to build a private cloud is very scarce. 1STACK and Starview is here to simplify everything. We have a complete stack of solution offerings to make the adoption easy, to make the journey easy for you. The reasons why you may want to build a private cloud instead of using a public cloud is many. As we spoke to our customers, we identified some of the top reasons why a private cloud makes sense. For some companies, the number one reason is data sovereignty. They may be in regulated business like banks, where it is impossible to keep data in the public cloud due to regulatory compliance. For some companies, an overhaul of legacy infrastructures and moving of legacy applications to modern cloud platforms is needed in order to take advantage of lower long-term operating costs. A private cloud can support a wide range of applications and use cases, from legacy applications such as ERP, databases, to high-performance computing, data lakes, AI machine learning, and also to support modern containerized applications. It is also a platform which you pay as you grow. Because of the virtualization, it allows you to add capacities linearly when needed. A private cloud brings you all the benefits of a public cloud internal to your organization. So what is 1STACK? And what does it comprise of? 1STACK is our complete solution stack comprising of hardware, software, and services to simplify the adoption of private cloud. We use OpenStack as the cloud software, and OpenStack is open source. We make sure that we curate and use the version that is production ready and support it throughout the lifetime. We choose the hardware platform carefully, the hardware that makes up the compute and the storage, plus the networking. And we aim to give you the best bang for your buck. With 1STACK, you are ready to build, to migrate, and to integrate. OneStack gives you many advantages over other commercial offerings: performance, features, cost, openness, and all under a single solution stack. One of the biggest advantages of OneStack is the openness of the solution. Everything is disaggregated. Every component in a stack is independent of each other. There is complete vendor independence and no lock-ins. In terms of performance, for example, we choose a hyper-converged server node that gives you the best in performance, the best in price, power, cooling, and footprint. Therefore, over the lifetime of your private cloud, you achieve the lowest TCO. For example, in a 2U HCI node, which you see on the left there with the drawers being taken out here. This is a platform in 2U that in total there is 256 CPU cores based on AMD EPYC chips. And we have integrated storage arrays with flash from offerings of Lightbits. As for networking, we use 200G and 100G connectivity to achieve the balance and the performance in the overall system. For your very high performance applications like AI or machine learning workloads, we integrate GPUs from NVIDIA. So these GPUs can be provisioned to your workload or to your apps, either via a pass-through mode, or the GPU can be virtualized to be shared among multiple workloads. And in terms of storage, we have the choice of either or and storage based on hard drives and storage based on very high performance NVMEs. These are the full flash arrays. For the NVMe storage, we work with Lightbits, and these are the industry's highest performance IOPS that can be rated in the millions. Now, as for networking, it is also open. We partner with EdgeCore to provide open and high performance network switches. And these switches can be 100G and shortly 200G and 400G switches when they become more common. The network operating system of these switches can be a choice as well, from open source Sonic to other commercial supported offerings like IP Infusion, for example. Today, based on 1STACK, we are open and we are ready to deliver all the benefits of a private cloud to you. And these are all achieved through open architectures to give you all the advantages of a cloud without the constraints of a vendor lock-in, and most importantly, without the high cost of commercial software licensing. So we are ready for you today. We invite you to sit back, relax, while we design and build, deploy a private cloud for you. So with this, I will hand off the next section to Dave of Define Technologies.
Excellent. Thank you, Drew. Good. So yes, hi everyone, and thanks Drew for the introduction. My name is David Power, and I'm the CTO here at Define Tech. And my own background is I've been working in the high-performance computing space for the past 20 years or so, which involves, engineering and architecting some of the world's largest supercomputing systems. And prior to that, I was a researcher in distributed genetic algorithms and artificial intelligence search strategies. So we've, this product came about a number of years ago when we, we started to identify that the adoption of cloud techniques and technologies was really starting to gain momentum within not just our own industry, but also other industries that we work with as well. So Define Tech is it's kind of a mixture of experts from various different verticals. We've got people within the organization who come from financial backgrounds, manufacturing and engineering, broadcast media. And the one common thing that we all had was that we all knew and observed that each of these industries were changing. Cloud had disrupted most verticals that were out there, and we saw the need for customers and organizations to reflect what the public cloud was doing, but to have that sort of agility and API driven infrastructure and software defined access and even containerization. These are all themes that we were identifying across all of these verticals. So what we do at Define Tech is we take open source products and build complex stacks on top of them. So we try and take away that administrative burden of setting up complex environments to allow researchers and users and scientists to come along and interact with our platform and spin up and create an appropriate environment for themselves without having to have the required, say, Linux administrative skills to go and set up these environments. So we fully believe in openness. We try and create our products so that they are incredibly interoperable with every other open source product that's out there. We believe in federated computing in the future, where people will be able to migrate and move workloads to the most appropriate environment. Private cloud is certainly one aspect of it, but we also believe in being able to leverage other resources externally for additional capacity on demand as and when it's needed. So yeah, we're an open organization with open principles throughout. The product we've been creating, of course, as Drew was saying, it's built on top of OpenStack, but we've been trying to create these application-specific verticals within our platform to allow organizations to quickly spin up and realize, very, very high performance, ease of use, and become more cloud native, and become more agile in terms of how they respond to demands from their internal organizations. It's a continuous development cycle, so more often than not, when we engage with a customer, we'll always learn a couple of things from them about how their environment works and what their specific requirements are. And we're continually feeding that back into our platform to ensure that we're maintaining, current trends and best practices within all of the verticals that we serve. Our core orchestration system is predominantly built to allow organizations to replicate that functionality that you get from a public cloud provider. Now, we also have tools and capabilities to actually import from these public cloud environments. So if organizations already have workloads which are running in some of the larger public cloud environments or even VMware, we can actually roll out these agents which will go into your instances out in the cloud, and we can then replicate them into our environment. Now, the same is true for actually pushing workloads back out into the cloud as well. So we don't try and lock people into using any one platform. We provide them with the tools and the techniques to be able to just push and move workloads to the most appropriate location for their needs. And the same is true even within our own platform. So we're a multi-cloud aware environment. We can spin up core and edge regions, and Drew will speak a little bit more about that when we come to the case study at the end about having a multi-region cloud environment where we can migrate workloads around to be adjacent and lowest latency to where the customer applications and data is being generated. At a high level, our platform, while it's based on top of OpenStack, and that provides a kind of an infrastructure as a service layer. So this allows you to do all of the compute, network, storage, provisioning in an automated API driven manner. But we've kind of built on top of that to provide more comprehensive stacks for users to just come in and consume as and when they require it. Now, initially we started and focused around the high performance computing space. But over the years, we've broadened that to support AI and deep learning. So we've done an awful lot of work with GPUs and NVIDIA. We've got support for big data, Hadoop and Spark workloads as well. And of course, with Kubernetes and Docker and containers, which are the the prevailing sort of technology for deploying and rolling out AI services. We've got full support for that type of environment as well. It's all backed by incredibly fast storage. So in terms of light bits and even some additional capabilities we bring ourselves, you've got a large amount of very, very fast storage, which can keep up with the demands of modern machine-driven workloads within environments. And of course, this ability then to push and migrate certain workloads as and when is suitable out into the public cloud environment. And the idea behind any cloud environment is really that you have the agility to respond to demands within your organization very, very rapidly. So even if AI and analytics are something that is just being initially considered and being prototyped within an organization, this platform allows organizations to future-proof their investment by being able to dynamically redeploy and reconfigure environments into these HPC analytical AI environments in the future as well. So you're not stuck with that. No environment ever remains stagnant for too long. The pace of evolution and change is it's staggering within this industry, and to be able to respond and adapt to those demands, you need an infrastructure that is dynamic and agile. That can keep up with those pressures from your users. So yeah, we kind of future-proof those investments by allowing organizations to have the flexibility of workloads across a dynamic infrastructure that's fully software defined and API driven. So with that said, I mean, I just wanted to kind of touch briefly on a couple of different use cases that we've seen out in the field and deployed. And one of the first ones I'll speak about is actually a national genomics research environment where a large amount of genomic sequencing was being conducted. Now, this actually happened to be a customer who had initially deployed their environment out in a public cloud, and they kind of over time slowly grew and scaled up to a certain point as where it had become quite expensive to continue doing what they were doing. They had sequenced a certain number of genomes, and they wanted to, their next target was about a 10x increase in the amount of genomes that needed to be sequenced. And when they extrapolated the costs for doing that, they quickly realized how expensive that would be running it predominantly in a public cloud environment. So one of the tasks that we were handed was to enable a kind of a seamless transition from a public cloud environment into a managed private cloud. So we spun up our environment, and initially we just imported all of their instances from the public cloud and spun up a replica cluster of what they were using for their R&D and sequencing workloads. And what this did was it allowed the users to first of all migrate to a very familiar environment. So there was no, apart from changing the IP addresses behind the SSH login nodes, nothing else changed. So we imported all of their applications, imported all of their operating systems, and gave them a clean, consistent view of what the public environment was. Now, they immediately benefited from significant performance increases due to the way that we optimize our hypervisors and ensure that we were running on the latest generation hardware. So immediately they saw significant performance improvements. But because we had that seamless transition, it allowed this customer to drain and turn off instances in the public cloud very, very quickly, and bring down their monthly cost bill by quite a significant amount. Once we had most of the users migrated off of the public cloud, we then started to look at provisioning these additional capabilities around the main cluster. So we started to spin out these virtual development environments for the teams that were actually going and creating and writing software. We had specific departmental clusters for R&D, for bioinformaticians, and for the general genomics research. We also started to upgrade different clusters as well. So they were running on quite an old version of operating system and scheduler out in the public cloud. And we were able to kind of spin up a new environment, test it with a new operating system, new compilers, new applications. And they wanted to introduce containerized applications as well using Singularity. So this would give them that bit more application mobility to allow them to go back and use public clouds in the event of high demand in terms of a very short turnaround. So we went through a process of containerizing a lot of their applications as well. Now, during the course of this, we also realized that they were running a number of infrastructure virtual machines on their VMware estate. So this was basic services like LDAP authentication, time services, DNS, and so on. So we were able to actually import those Windows-based services into our infrastructure as well, and further reduce their costs by eliminating that VMware license cost. And then kind of along the bottom, one of the other interesting things we had was they had a lot of the data sets that they were working with were incredibly sensitive. They had patient data and the data from end users and nationals, which was incredibly sensitive. Now, they were collaborating with a number of commercial pharmaceutical organizations as well, and they needed a very secure dedicated environment where they could actually go and experiment with the commercial organizations without the fear of any standard research, standard researchers being able to oversee what was going on. So again, because of the multi-tenancy capabilities that are inherent within OpenStack, we had this VXLAN encapsulated secure zone, which allowed for commercial organizations to come in and securely do their research without any other visibility externally within the cluster from those users. So that gave them a very safe way of collaborating in a multi-tenant sort of world. And then looking out across the land here, we actually created a user portal for the users who weren't as, say, familiar with the tools and techniques of using Linux command lines to access HPC environments. So we had a nice simple job submission monitoring and telemetry environment, which allowed users that were coming from using, say, a workstation into using a cluster without having to upskill too much in terms of learning lots of different Linux tools and techniques around batch scheduling and so on. So it was very successful in terms of our deployment, and we've got a couple of more customers actually in that space that will be coming online in the not too distant future. Another exciting area that we're working on in the lab is composable HPC. So if you look at what OpenStack can do, it's really taking hardware and partitioning that in a way where we can either run bare metal environments as individual servers or virtual environments as a subset of a physical server. Now the next evolution we see is this composable disaggregated technology, which allows organizations to essentially put in items like GPUs, memory, or even NVMe storage into these PCI pools, and they can be dynamically attached to hardware to reconfigure the hardware. So it's an evolution on reconfigurable computing, and it kind of changes the the financial models around how infrastructure is procured and upgraded and changed over time. Traditionally, I think you'd buy a server and it might be a static configuration, and that's it for kind of 3 or 5 years, depending on your support timeframe. And with this disaggregated composable infrastructure, you can take out expensive components like your NVMe, like your GPUs, put them into a PCI pool, and actually have our product orchestrate that environment. So if you think about AI and GPUs as a kind of a prevailing use case within the industry, they have a different release cycle to, say, the CPUs within your infrastructure. So there's always something that's evolving at a sort of a more rapid pace. Within our infrastructure, we can consume these devices on demand. So we can submit something to our environment. We can say we want 1 GPU, 4 GPUs. They can get dynamically attached to the worker node that you're conducting your research on, and they can be released back to the pool of infrastructure afterwards when you're finished with them. So it drives up the utilization of these expensive resources, and it also extends the lifetime of the rest of your infrastructure because you can dynamically upgrade it and reconfigure it in response to your users' demands for resources. So we think that this is a very exciting space and one that will be quite interesting over the next couple of years. And there's a few videos on our website about this in action as well with Slurm Workload Manager. Okay, getting towards the end of this now. So I mentioned multi-cloud a little earlier on. We have this edge and core capability within our platform, which allows local teams to run their own native cloud infrastructure, but it can be centrally managed and administered from one of the core offices. So we provide a single interface to allow you to manage a multi-region, geographically distributed cloud environment, and that's all part of the standard offering. Now, there's loads of other use cases that I just didn't have the time today to go through, but if anybody is interested, we have a remote gaming example up on our YouTube channel. We've also done some work recently with a stock exchange where we investigated the performance of virtualized and bare metal provisioning as a way of consolidating development and production environments within a trading organization. Again, a lot of the numbers are available on our blog, and we've also done a couple of videos with our partner LeoStream, who provide a nice VDI interface in front of OpenStack to be able to orchestrate and automate the provisioning of desktops and workstations for users in a policy-driven sort of manner for those guys as well. So lots of other great use cases that are available there. I've mentioned migration a little earlier on. So again, we have these tools which allow us to replicate from any of the major public clouds, or even things like VMware or standard KVM, or even just bare metal infrastructure. So if you have an existing setup that kind of fits into any of those source platforms, we have the tools that make it easy to lift and migrate or import into our OpenStack environment. And again, the reverse is also true, because these tools work in both directions. They allow you to also migrate workloads off of OpenStack and back into any of these other platforms as well. So we give you the freedom to, you know, put the workload in the appropriate environment for your business needs. Okay, and I just quickly wrapping up here, I've mentioned AI a couple of times. We've put together an AI reference architecture white paper, which covers in a lot more detail how to spin up and create and run these AI type workloads. We've always seen AI as one of the killer applications for HPC, and you know, within our platform we can do not just Slurm clusters, but also, you know, Kubernetes clusters in a very, you know, secure multi-tenant type environment with very, very high performance behind it to ensure that the GPUs are kept fed when you're running that expensive training operation. Or we have that edge capability to go out and do inference as a service closer to where your end users are and where the data is being generated as well. So there's lots more information on that, but yeah, Kubernetes and AI and GPUs are certainly a very exciting area, and I know one that will be spoken about a bit more by Babak at the Lightbits guys. So with that, I'd just like to say thank you for your attention, and I think at this stage I shall pass over to the Lightbits team. So Babak, over to you.
Thank you very much, David. Let me share my screen. So I'm Babak, Product Management Director at Lightbits. We've been working for a while with Design Technology and Starview. We have a few joint projects in production already, and this is truly a great team. David mentioned Kubernetes as well as OpenStack. We do have our current production environments are OpenStack, but today I want to cover more Kubernetes. I want to tell you a little bit about why it's good for your private cloud, and a little bit about why Starview selected LightOS as one of the building blocks for the joint solution here. So a quick introduction into Kubernetes. It was born 2014 at Google, and it does, you're probably all familiar. We have workloads, you put them into containers, you execute them, and it was designed initially for stateless applications. Stateless application doesn't mean that they don't need storage, it just means that they don't need persistent storage. That's the way it was designed. The benefits that it gives, and it was mentioned before, it lets you to scale up and down based on the workload. There's more workload right now coming in. You can bring up more instances into your Kubernetes cluster to handle all that new load, but the load then later goes down. You're able to scale down the application cluster running on the Kubernetes cluster. Another big advantage that Kubernetes gives you is portability. If there is planned downtime, unplanned downtime, the instances inside the cluster can move between a worker node to a worker node. That's how you call a server in the Kubernetes world. Now, when we look at modern applications, it's almost like part of the definition of what makes an application modern and cloud native is the fact that it's able to run under Kubernetes. And we have all types of applications that can run containerized inside Kubernetes. And you can notice already that some of them do need persistent data. And the other common thing, except for running under Kubernetes between all of them, is that the recommendation from the vendors of those applications is to run them on local flash to get the best performance. But it can be a little bit challenging. So in this diagram on the left, we can see a Kubernetes cluster. And the little white rectangles can show you the applications running in that cluster. And you can see that each one of the worker nodes, the servers inside the Kubernetes cluster, has a direct attached SSD. Some applications have their own replication layer. All that replication happens over the network, but also if something fails and the application decides it needs to build an additional replica because one of them is no longer available, everything happens over the network like this. We talked before about the two design concepts of Kubernetes. One is the scalability and the other one is the portability. But you can notice here that portability is hindered a little bit. You have your application, your pods being tied together with the storage. They suddenly become a unit and they need to migrate together, and to migrate data can take a long time. Also, if because of load balancing, you want to move one of your applications, suddenly maybe not all of the worker nodes are suitable because maybe they're configured differently because they were ordered in a different time frame. And maybe that one has spinning media and this one has NVMe storage and another one has a standard SSD. So that brings a lot of challenges on the portability. Also, the migration of an application, I mentioned that briefly, can take a long time. If you move the application, let's say it's a planned downtime, and you move it away from the node that you want to bring down, you need to wait for all the data to migrate to another worker node before it comes up and serve the workload again. The last point is the utilization. Now, NVMe storage, fast storage, is actually not cheap. And the way that you have your NVMe storage siloed into the compute nodes, the worker nodes, means that you usually, typically don't utilize them all the way from a performance point of view and from a capacity point of view. And if you do have spares, but a different node needs some of those capabilities, you cannot share them because they're locked into the server. Now, this is some data Lightbit Labs collected from prospects and customers, and we try to understand with direct attached NVMe, not necessarily Kubernetes, it can be bare metal or OpenStack and all sorts of deployments. When you put the NVMe drives inside the compute nodes, how much of it are you really utilizing? And on the left, we have the capacity utilization, which averages out to about 20%, which means 80% of the capacity is not being used. On the right side, we're looking at the performance utilization where things are better and customers end up using about 50% of the performance. The other side of it is that 50% of the performance is not being utilized on average. And this is where Lightbit Labs, LightOS can come to the rescue. So the first thing that we do is we take away the NVMEs and we put them into dedicated storage nodes running an NVMe TCP. That's the purple part on the top. And there are 3 of them, which is a minimum cluster. Now, the worker nodes continue to work the same. They're still running Kubernetes, they're still running those applications, but instead of having the storage inside each one of the nodes, they're now getting served over the network. And they're not really aware. and they're still getting great local flash block performance. In addition, they also get data services. Data resilience is one of them. Elastic RAID is one of the protection layers that LightOS has, which means that if a single SSD fails, the applications are completely unaware of it, and the storage target, the storage cluster, takes care of rebuilding, reshuffling, and making sure that the data is protected again, and service is uninterrupted. We talked about capacity utilization. Now you have a single pool where you can thinly provision only what you need. And even if you over-provision, it's thinly provisioned, so only what's really in use is being allocated. But I think the most value comes from the fact that now the storage is disaggregated from the compute, and instances can run anywhere and connect to the volumes. Recovery that before could took many minutes and even hours because you had to reshuffle all of your data. Now what you need to do is just restart the application and connect to the existing data that is just waiting and available for you, for the application. And what you gain eventually is higher uptime and increased SLA. The way we do that, the way that we integrate Lightbit's and NVMe over TCP storage with Kubernetes is a CSI plugin, similar to plugins that are available for OpenStack. Now, CSI plugin, we can say it's a nephew of Kubernetes. It was also born at Google, but the people who pushed for CSI, or with its full name, Container Storage Interface, are storage vendors. And I'll explain how it used to work. It used to work in a model that's called in-tree, which means I'm a vendor of storage product. I want Kubernetes to work with my product. I go and submit my code to the Kubernetes code base. And when the next version of Kubernetes comes out, those capabilities are now inside that next version of Kubernetes. There are some challenges, like what happens if I want to work with an older version of Kubernetes because I already have a running environment, but I want to buy new storage, for example. So the old CSI architecture changed gradually into a plugin architecture. CSI basically does two things. It defines a fixed interface that Kubernetes knows that when talking to storage, this is what it can do. This is how to say what it wants to do. And the plugin translates all that into the specific vendor-specific language of the storage product in the backend. And it doesn't matter which one it is. Kubernetes always talks the same language, and the plugin does the translation. The second thing is orchestrating the connections, which means you had a pod, a containerized workload moving from one worker node to another worker node. Kubernetes needs to also say, okay, I need to fire up a connection from this worker node to that volume. And the CSI does all of that. So it would seem like we have everything figured out. We have all the problems around taking Kubernetes, originally designed for stateless applications, and now it can work with stateful applications that need persistent data. But it's not really the case. So yes, there are a lot of solutions out there. There is Ceph, for example, an open source solution backed by Red Hat that can serve block and file. You have a lot of iSCSI-based products. You have various file systems and block-based products that are more proprietary and less standard. But typically, none of them can give you the local flash performance that LightOS from Lightbit Labs can give you. And some of them can, and usually it would mean that they can't give the same level of data services that LightOS can bring, like compression or data protection. And some of them will require you to use specialized technologies like RDMA for your network, which if you have is great, but if you don't, that means another big investment into this new project. We took some data, Ceph, from Red Hat, published on a cluster, and we can see that this is, for example, a product that can give you millions of IOPS, but at the same time, the latency under load is in the neighborhood of the full milliseconds, 3 milliseconds, 6 milliseconds. That's not really local flash performance, where we're talking about hundreds of microseconds. So we took the same data and we compared it to LightOS. On the left, we have the same data from Ceph. On the right, we have a comparable LightOS cluster. And we can immediately see that LightOS can provide a lot more IOPS under load, low latency under load. And we're not just seeing small advantages, we're seeing multipliers and huge multipliers in the performance, throughput, IOPS, and low latency that you can get. And all of that can be done with the hardware that costs less money. So to conclude on, again, why LightOS is great in general for when you need high performance block storage, and why Starview and Define Technology find LightOS as a good partnership for such workloads. We have the performance that we already covered. We have the flexibility. LightOS from Lightbeats Labs is the author of NVMe over TCP, which means any standard network can be used to use this storage product. There are rich data services from thin provisioning, compression, elastic RAID, etc. And because it's software defined, it means that you can build, or in this case, Starview can build the right configuration for your needs and for your workloads. And all of that can be done with a lower TCO because LightOS is optimized to use QLC NAND SSDs, which are cheaper per gigabyte. It can improve the endurance of your NVMe TCP storage, NVMe SSD storage. It aggregates them into a pool, which means that now you can direct the performance to whoever needs it, and you can direct the capacity to whoever needs it. And you can also scale the capacity and the performance independently from your compute, from your Kubernetes cluster, or OpenStack cluster, or your bare metal cluster. So that's it from Lightbeats Labs. I'm Babak again. Thank you.
Okay, thank you, Babak. At this point, I would just like to remind the attendees again that you may submit your questions using the Q&A button anytime that you like. I see already 2 questions, which we will answer during the Q&A session. We have one more, I think it's probably for you, Ju. How are the charges for 1STACK like, as competitors are charging based on licenses?
Okay, we do not charge based on licenses because we are using open source software. The OpenStack is open source, so there are no licenses involved. What we are charging are support, annual support. And these are based on nodes. In a typical 1STACK environment, you would have multiple nodes, a cluster of nodes on a compute or HCI, or nodes for storage, for example. And these are physical nodes that we are counting for support on an annual basis. If you look at software licensing of other companies, they are also charged on per node basis. But in many cases, there is a limit. They limit you on the number of CPU cores. So for example, if you use very high core CPUs, like the 64-core AMD CPU that we are using, a company that we know of will make you buy 2 licenses for that single CPU because the limit is 32 core. So for a single node, you need 2 licenses. For us, we don't care. We count on per node on support. So that is the reason why we prefer to use very high core platforms to optimize everything, including support. So that is how 1STACK charging and pricing mechanism is like.
Okay, great. The next question, being OpenStack, what was the framework used to perform hardening requirements from the government? I think probably Ju, for you again.
Depending on the requirements from the government, we will shut off unnecessary services, and perhaps will even introduce firewalls to limit external access. So we really have to understand what is the requirement before we can give specific answers to their questions. Do you have anything to add, Dave?
Yeah, I think just to complement that, I mean, besides the current project that we've worked on, we've deployed this solution in a number of, highly sensitive government locations and across the board. I think it's security and system hardening is sort of a core design principle of the product. So as you said, everything is shut down and restricted in terms of how users can engage and access it. Only the necessary services are allowed to actually have external access. All of the images as well that are injected into the environment go through a kind of a scan to ensure that they're meeting the minimum appropriate guidelines for security. So disabling simple things like password access to disable brute force password, restricting based on source IP in terms of how users access the system. It's all sort of best practices within the security industry to ensure that the system is hardened and secured when it's sitting out there on the public internet. So that is built into everything that we do from the ground up.
Okay, we have next a question on HPC. How do you think traditional HPC, high performance computing infrastructure, will change in the future, and how can we prepare for those changes? Probably for you, David.
Yeah, so I think we're kind of in quite an exciting time really in the HPC space. As I kind of said earlier, I think AI is one of the prevailing technologies within that space and one of the killer applications for HPC use. And what that's doing to HPC infrastructure is, on the one hand, it's introducing accelerators in very high demand, and that's changing how systems are architected overall. So traditionally you would have had an MPI based application which would use an InfiniBand fabric across a distributed CPU environment. But when you introduce accelerators, that changes the demands on back-end infrastructure such as storage. So to keep up with these evolving technologies within the space, you need to re-architect how you deliver that performance. And it makes NVMe almost an absolute mandatory when you're talking about workloads like this. I think we're also seeing a distributed approach towards HPC. So historically, there might have been large-scale centralized environments for large-scale research. I think as we look out into the future, we're going to see a lot more edge-based systems being deployed, and a lot of processing being done at the edge of infrastructure. And again, that changes the dynamic between how infrastructure is provisioned and having to take a more holistic view at a distributed architecture, and ensuring that there's performance optimizations across the board for that sort of an environment as well. And finally, I think we're also quite excited about this whole disaggregated and composable infrastructure approach. So being able to split out the core components of your infrastructure and put them into a kind of an API-driven composable language to allow hardware to actually be dynamically aggregated and configured in response to the changing workloads. Certainly, it's a very exciting technology to play with in the lab, and we see a lot of very interesting use cases around that sort of technology as well, which should be adopted in the not too distant future. So it's yeah, exciting times, and yeah, lots of change on the horizon.
Okay, another question on charges. 1STACK looks like a full stack solution. Is it possible to try the software stack of 1STACK without purchasing the accompanying hardware? How would you charge the software aspect of 1STACK? So, Ju.
Okay, let me take this question. We decided to offer a full stack solution in order to simplify that decision process of putting things together. What works well with what versions of hardware works well with the software, for example. In our experience of using OpenStack, we found that we need to be very, very careful in choosing the right hardware platforms. Because we have encountered many issues through our experience, and some of them are basic hardware compatibility issues, hardware and software compatibility issues, putting the hardware together in order to achieve a balanced system, because no point to have a very high and fast CPU, for example, but we get limited by the I/O, and which again slows everything down, and we're just throwing money away. So it's very important to achieve a balanced system in order to optimize everything. And on top of that, we have also seen issues of heat. And if this is not addressed properly, heat can cause serious implications to the performance of the compute cluster. So the answer is yes, you can use the software independently. The choice is yours, but it would make our job a lot more complicated, because different hardware platforms will behave differently. We will recommend the hardware platforms that you choose our hardware platforms in order to be able to get the best out of everything. And the next question is, how do we charge the software aspect of 1STACK? The software is based on OpenStack. There is no licensing needed on that. Instead, we charge the annual support for the software. We work with Define Tag to make sure that patches and upgrades are made available to you, and that these patches are suitable for your environment, fully tested, etc. So that is the beauty of open source. If there are engineering capabilities available, you can do yourself without paying anything. But it will also mean that you need to have very in-depth knowledge of what to do. And it can be very complicated. So the support will take away all the anxiety of deciding what to do, what software patches to be patched, and to keep your system running in the most optimal fashion.
Okay, great. Next, we have one for Lightbits. Does LightOS run inside the K8 cluster? Babat?
Yeah, so I'll take that. The answer is no, and there are multiple reasons why not. So the first one is that LightOS is not specifically designed for Kubernetes. There's a lot in it that makes it ideal for Kubernetes, and they work really well together. But at the same time, it could be a bare metal solution, OpenStack solution, etc. The second reason is that even when you do use Kubernetes and you use LightOS for that Kubernetes environment, you don't want your infrastructure to be dependent on Kubernetes. You do want to have some level of separation in order to gain higher uptime or just better stability. I hope that answers the question.
Okay, next one. Being open, are you subjected to the same zero-day vulnerability that are also exposed to the kernels used by RHEL, for example? How does 1STACK LightOS deals with reported vulnerability?
I think the best person to answer this will be Dave.
Yeah, sure thing. So unfortunately, zero-day vulnerabilities are, a feature really of open source technologies and any technologies, Windows as well. The best practice for addressing these is just a good policy around security in front of your environment. Now, I mean, we have customers in the financial space, for example, that are running this platform across different regions and different zones, and absolutely none of it is exposed to the public internet. So by being able to put this environment in a private area and keep it off of the public internet, you are that bit more secure inherently than you would be perhaps on a public cloud environment. So that physical separation from the internet becomes a nice barrier to kind of help avoid those. Now, on the other side of it as well, we do actually have organizations that are running this platform as public services. And, again, the best practices there are to completely restrict all of the underlying access to your environment. So you'd often have like a VPN with multi-factor authentication behind it just to get into your environment to manage it as an administrator. None of the underlying undercloud is exposed to the internet at all. And then when you are running services, only those services ports are actually exposed to the internet. So the systems, SSH and so on, all of these are hidden behind encrypted APIs and SSL certificates. And they're hardened in a way that prevents users from even being able to brute force their way into it. So the best protection against these zero-day vulnerabilities is actually a solid layer of protection in front of your environment to prevent unauthorized access to the environment to even expose those vulnerabilities in the first place. And again, when it comes, I can see the next one's coming up about the patching. So we maintain a registry of containers for all of the cloud services that we provide as part of the stack, and this is tested on a daily basis in terms of our GitOps environment. So we build, test, and validate these environments, and as and when new patches need to be injected, they're injected into those, and they're available to our customers to then go and roll out in a kind of a rolling update. So there's zero downtime with these, apart from when there's kernel updates. But we keep our backend patched and up to date and made available for customers out in the field as well.
Okay, next we have, is LightOS an essential part of the LMX cloud? We actually have Baba who is already typing the answer.
Yeah, but I'll answer quickly.
Okay.
The first question is what you're trying to achieve with your cloud. And if what you're trying to achieve requires a high performance, low latency storage, then it would be recommended to use LightOS. But no, LightOS is not mandatory. And some of the solutions we have today have LightOS in parallel to other storage solutions that don't require high performance, for example.
David, you want to add anything?
Yeah, no, I mean, just to complement what Babak said, it's certainly something we recommend whenever there's demanding workloads running on top of your environment. It's balancing the architecture and ensuring that high performance CPUs or high performance GPUs have an appropriate level of storage to feed those to keep them busy. Just makes financial sense. You don't want to be you don't want any expensive components within your infrastructure sitting in an IO wait state for some legacy HDD based storage to come in there and work with it. But as Babak said, it's a very modular solution, so you can pick and choose the components that are most appropriate for your environment and optimize for your costs and optimize for that environment. So it's a recommended technology that we've certified and work with and love working with. But there's plenty of other options out there. If you have existing storage, for example, that you want to integrate, if there's an OpenStack plugin for that existing storage, it might allow you to continue to sweat those existing storage assets for a bit longer, while you perhaps revise your strategy around an all-flash future environment.
Okay, next, besides those segregation that you mentioned, how fast are those vulnerabilities being patched?
Yes, so I sort of mentioned this a little bit earlier, but we have an internal GitOps environment which actually goes through a rebuild and functional validation of our entire cloud stack on a daily basis. And this will actually import additional CSV bug fixes whenever they're made available upstream. So we have this continuous environment which was made available to our customers. So as soon as patches are made available, they're rolled in, built into our environment. We have a full suite of functional tests which validate and ensure that everything is still working and functioning as it should. And then this ability to roll out these updates in a non-disruptive manner to ensure continuity of your service, even when these patches are being applied.
Okay, we have next one. What is the minimum setup of the 1STACK solution?
I will take this question. Cloud platforms works best when we have more nodes. The reason is distribution, and also the other reason is parallel. So with more nodes, at performance and reliability actually goes up, because a single failure of one node does not bring the entire service down. It is self-healing, but that only works when there are sufficient nodes out there.
I can step in here as well, Drew, just in case. Yeah, but I mean, in terms of a minimum setup, I mean, we run workshops and training academies where we actually spin up virtualized environments within our own internal lab OpenStack environment, and we can actually run a fully functional featured version of our platform in a VM with 32 gigs of RAM and use that for demonstration and training purposes. Now, in reality, in the field, I think as you said, resilience, and if it's running in a production environment, the minimum starting point is really a deployment node and then 3 hyper-converged systems to run all of the core services in a redundant manner. But we can scale out from that, and that could be a small edge region. And you can then get into quite complex architectural discussions. But we can run on a very, very small VM for investigation purposes, and a deployment plus 3 hyper-converged systems is probably the minimum starting point for a production site.
Thank you, Dave.
Okay, next, how does LMX enable transparent migrations between different cloud types?
Sure. So one of the products that we work with is an organization called 1STACK. And this has a number of tools within this environment, which covers, P2V, which is physical to virtual, V2V, which is virtual to virtual conversion. So we can actually take things like, VMDK images, convert them into QCOW, import them back into OpenStack, push out to other OpenStack environments. So, using these tools, we have a lot of the flexibility around migrating between different cloud environments. So it's fully API compliant with all of the other cloud environments, and it can do things like disaster recovery out to external clouds as well. So if you did have, say, a single region and something catastrophic went in terms of your network connectivity or power or anything like that, we could actually disaster recover over to a public cloud environment for critical services within your environment, provided that there's an appropriate level of synchronous transactions across your data sets in the background of those VMs. So yeah, there's a couple of ways of handling this. Kubernetes, then, because we're able to actually spin up these Kubernetes environments, that actually also has quite good capabilities in terms of being able to migrate different containers out to different Kubernetes environments. So that's also another way of addressing migration between different cloud types as well.
Thanks. Next, what size environments is like OS ideal for? Babak, you want to take that?
Can you repeat?
What size environments is like OS ideal for?
Excellent. So cluster-wide, we're talking about anywhere from 3 nodes to 16 nodes currently. And then each node can start from around 32 terabytes and go up to 300 and something terabytes raw. The numbers are actually in the replies in the chat. So for a complete cluster, we're talking about a minimum of about 100 terabytes, and it can grow up to 6 petabytes. Yeah, that's it.
Okay. All right. Thank you very much for the very, very lively Q&A session. We have actually run out of time, so we'd like to thank you once again for joining us today. We've now come to the end of our webinar. We hope it has been a good use of your time. Kindly help us to complete the evaluation survey. You should be automatically directed to a survey page in your browser once we end the webinar. With that, we wish everyone a great rest of the day. I will now end the webinar. Goodbye.
Thank you, guys. Goodbye.
Thanks, everyone.
Bye-bye. Thank you.